I will be discussing the design of an experiment that explores the different factors influencing water treatment techniques using alum and activated charcoal. In order to better understand the motivation for this work, it is important to understand the depth of the global water crisis. 1 in 10 people globally do not have access to clean water, and every 2 minutes, one child dies from consuming unsafe water. This demonstrates the need for the development and improvement of water treatment technologies. Current processes include coagulation, flocculation, sedimentation, and filtration. This experiment focuses on coagulation using alum and also filtration using charcoal. I can first go ahead and discuss the first part of the experiment involving the use of alum to remove inorganic particles from wastewater. Alum is a common industry coagulant, and the form we use in this experiment is called aluminum potassium sulfate. We simulated wastewater using kaolin clay and deionized water. The wastewater is placed in a beaker, and then the optical density of it was measured using a spectrophotometer. Before the alum is added, the particles are suspended colloidally within the solution due to their negative surface charge. When alum is added, the positive cations from the aluminum interact with the negative surface charge in a process called charge neutralization. This allows the kaolin particles to attract to one another and actually interact, and over time they form larger flocks that are able to sediment to the bottom of the beaker. Over a time period of 60 minutes, we gathered samples from the top clear portion of the beaker and measured the optical density to compare with the initial values. I can now go on to introduce the charcoal adsorption-based method of this experimental design. This mechanism relies on adsorption because of the high surface area of charcoal. The complex porous structure of this adsorbent allows for organic molecules to enter and be sort of trapped within the charcoal. In this experiment, we use a PVC pipe and we packed it with charcoal sandwiched between sand to hold it in place. We used food dye to simulate the various types of organic molecules that can be found in wastewater. We measured its optical density before the elution took place, and then after 30 minutes of elution through the column, the optical density of the resulting clean water was measured again. In this experiment, for the alum portion, for the coagulation portion, the kaolin concentration and the alum concentration were varied, and then for the adsorption charcoal-based technique, the charcoal type and size were varied. I can first go on to summarize the results for the coagulation portion of the experiment. The first variable is the kaolin concentration. We can see that as kaolin concentration increases from 0.1 to 1 grams per liter, that there is an increase in kaolin removed. This can be explained because there is a large amount of kaolin particles available, and therefore the coagulated flocks are larger and able to sediment to the bottom of the beaker more quickly. We can also take a closer look at what happens over time. We can see that over time, a larger percentage of kaolin is removed. This aligns with literature that states that over time, more charge neutralization occurs because there's more interaction between positive aluminum cations and the negatively charged surfaces of the kaolin particles. It is also important to evaluate the amount of alum needed in these systems. From these results, we can see that as alum concentrations increased from 1 to 20 grams, that there is an increase in percent kaolin removed. This is supported by literature that states that the larger the amount of alum, the higher the amount of cations available to participate in charge neutralization. We can also note that between the higher concentrations, 15 and 20 grams, that there is minimal difference seen. This can be attributed to a phenomena called charge reversal. This occurs when there is actually too much alum used for coagulation. This causes a buildup of positive ions on the surface and actually causes the particles to repel one another and prevents coagulation. So this lets us know that there's actually there can actually be too much alum that can be used. Lastly, we can discuss the results for the adsorption-based charcoal technique of the experiment. We can see here the smallest charcoal type used, 20 to 40 mesh. Then we have the mid-size, 5 millimeters, and the largest granules used were called aquarium sized. We can see that for the largest charcoal granules, there is much less food coloring removed than with the smallest charcoal size. This is supported by literature that states that having a high surface area available for adsorbents is very important to the amount of contaminants that can be adsorbed. We also can explain this through the idea that smaller particles are able to pack more closely within a column, and therefore the water cannot pass through the column without actually passing through the adsorbent itself. And finally, in conclusion, we can summarize that having a higher contaminant concentration results in larger flocks that can be removed more easily from the wastewater. We can also summarize that a higher alum concentration results in more kaolin removed. And finally, we can also understand that using a small charcoal size results in a greater removal of contaminants. Thank you.